In this video, we're going to go over pH curves and all the information that we can get out of them. So the first thing that we can tell from looking at a pH curve is going to be whether the titrant or the sample is an acid or a base. So with this, your sample solution, you're going to be able to tell what pH it's at from where the pH curve starts. Whereas with the titrant, you're going to be able to tell what pH that is at the end of the pH curve. Okay, so just as a reminder, the pH meter, which is the instrument that measures pH as you do a titration, that is put in the sample solution. So if you wanted to draw a little diagram of what this looks like here, so we've got our Erlenmeyer flask, which is where you have your sample solution. Okay, and then you have your little pH meter put in. Okay, and this is what you start off with. Okay, so that's why the pH meter is first going to detect what pH your sample solution is at. Right, and then because you are doing a titration, you have your burette here. Okay, so as you add in your solution, your titrant from your burette into your Erlenmeyer, so as it mixes in with your sample solution, slowly your pH of your solution in your Erlenmeyer flask gradually becomes more like the pH of the titrant. So let's just kind of write out what I said. So pH meter is in the sample solution, which is put in the Erlenmeyer flask. So an Erlenmeyer flask is just a conical shaped flask. Okay, and then we're going to add over here and ends at titrant pH. All right, the next thing that we can figure out by looking at a pH curve is where your equivalence points and buffering areas are and how many of each there are. So the flatter areas, those are going to be your buffering areas. The only one that wouldn't be a buffering area is the last flat part of your titration curve. Now for endpoints, which for the purposes of this class are going to happen right at the same time as the equivalence point, those are going to occur at the middle of the steepest areas of your titration curve. Okay, so let's just write out what I said as a little note here. So equivalence point, which that specifically refers to how much volume of your titrant that you've used. And that's usually in milliliters. Again, for the purposes of this class, we'll say that the equivalence point happens at the same time as the end point. However, the endpoint is going to refer to the pH of the solution. And the endpoint also occurs at when your indicator changes color. And the color change that you're looking for is the in-between color. So for example, let's say we looked at phenolphthalein. So because it goes from colorless to pink, the endpoint would occur when phenolphthalein becomes this light pink color. So that's what I mean by color change. All right, so each steep region, which is either, we could call it the equivalence point or the endpoint, just depending on whether we are referring to the volume of titrant, so I should say titrant, not titration, used, or the endpoint, which refers more so to pH or the color change of the indicator. So each steep region refers to an acid or a base losing or gaining one proton at a time quantitatively. Okay, and whether you're talking about an acid or a base or losing or gaining one proton, it just depends on what your sample solution pH is and what your titrant pH is. So as a general rule, only quantitative reactions, so those are reactions that like your reactants react completely and they are used up to create products, so you only have products remaining because all of your reactants got used up. So as a general rule, only quantitative reactions produce detectable equivalence point in an acid-base titration. So therefore, the number of endpoints, that's going to tell you the number of quantitative reactions. The next thing that we can tell by looking at a pH curve is we can also decide on what indicator would be best used for each endpoint. So how we're going to choose indicators is that you want to focus on which indicator is going to make you stop the titration as close to the equivalence point as possible. So therefore, the endpoint pH in your titration curve should be as close as possible to the midpoint of your range for your indicator. Okay, so just to summarize that up, so your endpoint, that occurs at the middle of the steepest part of your graph. And there can be more than one steep part of your graph. It kind of just depends on what is in your sample solution. Okay. And then to select your indicator, you're going to choose an indicator where the endpoint occurs in the middle of the range of the indicator. So this will make a bit more sense once we actually get into an example. All right, so let's just take a look at this pH curve where we have boric acid is being titrated with a sodium hydroxide solution. So even without looking at the pH curve, the title tells you a couple of things. Okay, so you're going to want to look out for the titrated with, because after those words, whatever solution comes after those words, that's going to be your titrant. So that means what came before, that's going to be your sample solution. So we can even double check this looking at the pH curve. So the pH starts off quite low, right? Which would correspond to an acidic pH. And looking at what we've been given in the title, well, it'd make the most sense that our sample would be the boric acid. Okay, so where your pH curve starts, that is going to show you the pH of your sample solution. So I'm going to abbreviate solution to SOLN, is boric acid. Okay, and then looking at the very end here, so the pH at the end of your curve, that's going to correspond more closely to the pH of your titrant. Now, since this is approximately a pH of 11, it makes sense that our titrant is sodium hydroxide. That's a strong base. How we know it's a strong base is any metal ion that's paired with hydroxide is a recipe for a strong base. All right, so let's look at our buffering areas. So these are going to be the flat areas of our pH curve. The only exception being the last flat part, that is not a buffering area. Any flat part but the last flat part is a buffering area. So right here, this plateau, that would be our first buffering area. You could say buffering area or just buffer area, same thing. So this is where we're going to have our first equilibrium reaction. So we're going to have an equilibrium here. So this means when we are writing out the reaction for a buffering area, because it's at equilibrium, at least temporarily, that means you would have to write the equilibrium arrows. All right, so we've got this steep area here. So the middle of this steep area, that is going to be where our first endpoint is. Okay, so if I say kind of right around here is the beginning of the steep part, and then right around there is where the steepest part kind of ends in this section, I'm going to eyeball the middle in between these two lines to figure out where the endpoint is approximately. So I would say the middle of the steep part is kind of just under this line that says a pH of 4. So if I draw a straight line over, right, we could say that that occurs at a pH of 3.9. So that would be where our first endpoint is. And then if I draw a straight line down from there, that'll tell me the volume. So this would be the first equivalence point. Okay, but I really don't need these lines here. What matters is where the first endpoint and first equivalence point is. Okay, now what I should also add in along the x-axis here is this is telling us the volume of titrant used. So that's in milliliters. And the y-axis tells us the pH. So I'll write that in over here. Okay, for our next flat part, that's occurring around here. So this is our second buffering area. So again, we have another equilibrium. So if we were to write out the reaction, or the reaction that's at equilibrium here, we would have to make sure to write the equilibrium arrows. Okay, but again, I'm gonna, like for the second endpoint, what I'm gonna do is I'm gonna mark out some lines to just help me eyeball the middle of the steepest part. So I'm gonna say the middle of the steepest part, kind of just above this pH line of 8. So due to my snap grid not letting me draw this line where I want it to be, I'm just going to have to freehand it here. And I'll just try to do it as straight as possible. So here's where my second equivalence point would be. So remember, equivalence points, they tell you the volume of titrant. So they tell you the volume of titrant that's used to get to that point. And then our second endpoint is right here. All right, so between 8 and 10, so the middle of that would be 9, so right around there. So I would say this is probably at a pH of 8.2, 8.3, somewhere around there. Okay, for the equivalence point volumes, you do just got to be aware that like each one of these numbers, like the tick mark comes before it there. Okay, so for the first equivalence point volume, I would say that's probably somewhere around 28, 29 milliliters. So we'll say about 29 milliliters. All right, so 50 is right here, 55 is right there. So for the second equivalence point, I would say that's happening somewhere around like 53 milliliters. If you did say 52, there is a little bit of wiggle room for this, just because there's not a grid that makes it easy to tell for sure. But yeah, there is a little bit of wiggle room with this. However, you got to be in the right kind of ballpark here. Okay, if you said this is at a pH, or sorry, a volume of 50 milliliters right here, then you would be wrong. Okay, last thing I just want to say, this last flat part, not a buffering area. Okay, now in between our first equivalence point volume and our second one, the volume to get to the second equivalence point will roughly be twice that of the first equivalence point volume. So that's not a hard and fast rule. It's just to kind of help you kind of estimate where the second equivalence point should be. Okay, so this was just an introductory example. Okay, I didn't want to go into what are the specific equilibrium reactions or the quantitative reactions, just because there's not a whole lot of room here, but also I didn't really want to overwhelm you guys with all of the information here. So this was just an introductory example. We are going to get into the nitty-gritty of all of the reactions in the next example here. Okay, so for the next example, it is kind of put between 2 pages here. So we've got 25 milliliters of a 0.5 mole per liter sodium carbonate solution that's titrated with. So that titrated with, that tells you that what comes after it is the titrant. So our titrant is the 0.5 mole per liter hydrochloric acid. Okay. Now with sodium carbonate, that would be that. Okay, and for titrations, you are assuming both your sample solution and titrant, both of them you can assume are aqueous. So in order to be able to write out these reactions, we are going to have to do a species list. So we're going to be following the steps that we went over previously with writing Bronsted-Lowry reactions there. So the steps that I'm talking about, they happened quite a while ago. So the steps that I'm talking about, they were on page 46 of this note package. These are the steps that we're going to be going through. So we're going to be writing a species list out, and from that species list, we're going to determine what is our strongest acid, what is our strongest base, and then we'll use that to help us figure out what our quantitative reactions are as well as our equilibrium reactions. Okay. So with our species list, for our first substance, sodium carbonate, that is an ionic compound. Since it's aqueous, that tells us that it's soluble in water. An ionic compound that's soluble in water is going to dissociate. So that means it's going to break up into its cations and anions. So the cations that make it up are the sodium ions. And then the anions are carbonate ions. Oop, that should be 2 minus. Okay, because these are solutions, we do have to say that water is present. Okay, and then it is being titrated with hydrochloric acid. Now, if we go to our data booklet, and I'm on this would be page 8 here. Okay, so hydrochloric acid, it is one of our 6 strong acids. So anytime you have a strong acid, the fastest reaction that's going to occur is between the strong acid and water to produce hydronium. Okay, so what's happening here, or the quickest reaction that's happening here, is hydrochloric acid is reacting with water to produce hydronium ions and the conjugate base of our acid. Okay, so what I have for my products over here, that is going to be what I put in my species list, because this is a very fast reaction. So you're going to have the products produced from this in your species list. So I'm going to say hydronium and chloride ions. So you know to do this when you have a strong acid here. Okay, so now we're going to look at the table on page 8 and 9, and we're going to figure out where all of these are on the table. So just to let you guys know, you're not going to find sodium on the table, so I'm not even going to worry about that, but let's try and find the rest. The reason why I know I'm not going to find sodium is because there's no metal ions on that table. Okay, so I'm going to clean this up just a little bit here. We do have water, so I'll circle that one again. And I just need to see what else I need to clean up here. Okay, so the other thing that we have are carbonate ions. So I'll circle that. We also had hydronium. I'll circle that, and then chloride ions I'm going to find right there. Okay, so to determine our strongest acid, I'm going to put my finger in the acid column, and then I'm just going to trace it down until I hit my first chemical species in my species list, which is hydronium. So that's going to be the strongest acid. So I'm going to label this SA for strongest acid. And then I'm going to do a similar process, except for from the bottom right-hand corner for the bases. Okay, so I'm going to put my finger here and then just trail it up. And then the first thing that I run into in the base column from my species list, that's going to be my strongest base. So the carbonate ions is my strongest base. So that's what's going to be the main actors in my chemical reactions here. So looking at this titration curve, okay, we'll use this information that we just figured out. We'll use it in a little bit here, but I just wanted to mark out some areas. Okay, so starting off with this pH curve, so each one of these tick marks is a pH unit of 1. So if this one is 14, 13, 12, 11, so this starts out about a pH of 11, maybe 10.9, 10.8. So we'll say a pH of about 10.9 is where it starts out. Okay, and then over here is where we have our first buffering area. Okay, so In this square box right here, that's where we're going to write our first equilibrium reaction that represents the buffering area reaction. So we'll just call this the buffer reaction, or buffer reaction number 1. Okay, so what we're going to do is we're going to take our strongest base and our strongest acid, and we're going to write an equilibrium reaction to represent this. So I'm going to start off with hydronium, react it with the carbonate ions, and because it is a buffer reaction, that's going to be an equilibrium. And remember, we're only transferring 1 proton at a time. Okay, so if I imagine hydronium with 1 less proton in it, that's just going to be water, which has a liquid state. And then if I imagine the carbonate ion with 1 more proton to it, that's going to be hydrogen carbonate with a 1- charge. Okay, so again, how I'm figuring out the charges here is for water, that started out as hydronium, which had a 1+ charge. It lost a proton, so it lost a 1+ charge, which is equal to 0. That's why water is neutral. Okay, how I figured out the charge on hydrogen carbonate was carbonate ions. They started out with a -2 charge, or a 2- charge, however you want to say it. It gained a proton, so -2 plus 1, that's going to give me -1. So that's how I'm figuring out the charges. So whatever you do, do not forget about charges and don't forget about states. And you also have to be able to predict what your products are. Okay, so these are just more Bronsted-Lowry reactions that we're writing. So I'm going to write a little note. So the buffer area reactions, those are equilibrium reactions. They are not quantitative. If it was quantitative, I better spell that right. If it was quantitative, we would just be using a single forward reaction arrow. Okay, so point A, that is the middle of our first steepest part of our curve. So that's going to be our first endpoint. Okay, so that's occurring. So if this is a pH of 7, that means this is a pH of 8. It's coming in just under halfway between a pH of 8 and 9. So I'm going to say that this is happening at a pH of 8.4. So the first endpoint is going to be when my base accepts its first hydrogen. How I know that it's the point in which the base accepts its first hydrogen is because we're starting with a super basic pH and we're like moving towards a more acidic pH. So that can only happen if you're adding in more acid. Where is the acid coming from? Well, it's coming from because we're titrating with hydrochloric acid. Okay, so we're adding in hydrochloric acid from the burette. So what this first endpoint reaction is going to look like, it's going to look very similar to what we wrote for the buffer reaction, except for instead of equilibrium arrow, it's going to be a quantitative arrow because endpoints indicate that you have a quantitative reaction happening at that point. So remember, water, the state of that is always going to be liquid. It is not going to be aqueous. Because if you put water as aqueous, basically you're saying water is dissolved in water, which doesn't really make a whole lot of sense. You just have a whole lot of water there. All right, so that is our first quantitative reaction there. So moving along on this pH curve, this next area is our second buffer area. So our second buffer reaction what we're going to do is we're taking our conjugate acid of our base and we're continuing to react it. Okay, you do not take the conjugate acid, or sorry, the conjugate base of your acid for this. And the reason why we do this, we focus on the conjugate acid of our base, is because there is a lot of this still present here. Okay, because our base that produces our conjugate acid, that was in our sample solution. That's how I know that there's a lot in there. Okay, and so we're reacting this with our titrant, or with our strongest acid, so hydronium. Because it's a buffer reaction, we write equilibrium arrows, okay, and we are still transferring from our acid to our base. So we're transferring our proton from our acid to our base, because you can remember that acid, A for away. Proton goes away from the acid and comes towards home base. So we've got water for one of our products, and then I'm going to imagine hydrogen carbonate with one more proton on it, so that's H2CO3, aqueous, and that'll have a neutral charge. So point B is going to be our second endpoint. Okay, and that's going to occur, it looks like that's at a pH of 1, 2, 3, so a little bit above halfway between a pH of 3 and 4. So I'm going to say that's happening at a pH of 3.6. Okay, and what I haven't been mentioning is just the equivalence point volumes. So for the second endpoint, the equivalence point volume of that would be 50 milliliters. The equivalence point volume of the first endpoint would have been 25 milliliters. Okay, so if you're wondering what this centimeters cubed is, that's like 1 centimeter cubed is equivalent to 1 milliliter. All right, so at our second endpoint, that's where we're going to have our second quantitative reaction. So it's going to be similar to our buffer reaction, except for instead of an equilibrium, it's going to be a quantitative reaction. Okay, and then just remember that this last plateau here, it's not a buffering area. Keep in mind though, an equilibrium can happen. We're just not going to rate it out, and it's not a buffer area. Okay, so next we're going to talk about the possible indicators and their color changes for the first endpoint. So like I said, the first endpoint, this happened at around a pH of 8.4. Okay, so for choosing our indicators, we want to choose an indicator in which 8.4 is somewhere in the middle of the pH range for an indicator. Okay, so let's go to our data booklet, page 10. I'm going to clean this up some. Okay, so I'm noticing that some indicators that would work, so phenolphthalein, 8.4 is right in the middle. It's not the exact middle, but it's in the middle of this range. Okay, another indicator that would work well would be thymol blue. Okay, 8.4 is in the middle of its second range there. And then another indicator that would work well would be cresol red. So we do have a few different answers here. Okay, so let's just start out with talking about cresol red and what's happening there. So for the color changes, you're going to want to talk about the color that it starts out with at the beginning of the titration, and then what color it changes to at the first endpoint. Okay, so our pH curve, or our titration, it started out at a pH of 10.9, and the first endpoint we said occurs at a pH of 8.4. So 10.9, that is at a pH of above 8.8, so that means cresol red is going to be red starting out. But then at the endpoint, that's at a pH of 8.4, so that's in the middle of the range. So the color of it is going to be the in-between color. So the in-between color between yellow and red is going to be orange. So it's going to go from red to orange. So typically the second color that you mention for your color change, so that's occurring at the endpoint, it's going to be an in-between color. So it's going to be typically a secondary color unless you're talking about an indicator such as phenolphthalein, which goes from colorless to pink. So the in-between color would be a light pink. Okay, next indicator that I'm going to talk about is thymol blue. So again, starting out at a pH of 10.9, going to a pH of 8.4. So 10.9, that's at a pH above 9.6, so it's going to start out blue. 8.4 is in the in-between range, so this is going to be the in-between color. The in-between color between yellow and blue is green. So it's going to go from blue to green. Okay, I'm going to have to write phenolphthalein over here because I don't have a lot of space. Okay, so starting out pH of 10.9 to 8.4. So 10.9 is above a pH of 10, so it's going to start out pink. 8.4 is in the in-between range, so it's going to be the in-between color, which is light pink. So pink to light pink. Okay, possible indicators and their color changes for the second endpoint. Okay, so for the second endpoint, we'll say, like, you'll want to look at the previous plateau. Okay, so we'll say, like, that one happened around a pH of 7. And we said that the second endpoint happens at a pH of 3.6. So we're imagining that we're recording the color changes of our indicators from 7.0 to 3.6. And to choose our indicators, we got to make sure that the indicators that we choose, 3.6 is in the middle of their range. Okay, so 3.6 will be in the middle of the range of methyl orange. And it doesn't look like there's any other indicators that have 3.6 in the middle of its range. So we're going to leave it at that. So methyl orange is our indicator for the second endpoint. So imagining that it starts out at a pH of 7, going to 3.6, so 7 is above 4.4, so it's going to start out as yellow, and then 3.6 is in between, so it's going to be the in-between color, so in between red and yellow is orange. So it's starting out as yellow and going to orange. All right, the other thing that we can determine from pH, looking at pH curves, is we can also determine whether the acid or base is strong or weak by looking at the equivalence point. Okay, so we've got lots of examples here. Now remember, the sample is going to be what your pH starts out as. So the starting pH is going to be the pH of your sample solution. So looking at this first titration curve, we have a strong acid being added to a strong base. Now, looking at the pH curve, it starts out at a pH of 14. So that tells us that the sample is a strong base, which I'm going to abbreviate to SB. Okay, so when you have this kind of wording here, a strong base is being added. Okay, whatever is being added, that is your titrant. Okay. And we can double check this because the ending pH is going to be closer to the pH of your titrant. So we can tell here because it ends at quite a low pH. A strong acid was a titrant. Okay, and when you titrate a strong base with a strong acid, your endpoint, which happens at roughly the same point as the equivalence point. Okay, endpoint just refers to pH, whereas equivalence point refers to volume. Okay, so the endpoint for a titration between a strong base and a strong acid is going to be at a pH of 7. So that's the important part here. So the pH of an endpoint of a titration between a strong base and a strong acid is going to be 7. Okay, same for a titration between a strong base and a strong acid. It will also be at a pH, the endpoint will also occur at a pH of 7. So sometimes I've been writing endpoint as NPT or just writing the whole word out. So just be mindful of that. Okay, so with this, our sample solution, since the pH is quite low, that means the sample is a strong acid. And then the ending pH is quite high, so it's right around 13, 14. So that tells us that the titrant was a strong base. Okay, now it is saying 25 milliliters. That's just for a generic example. That doesn't mean for every single strong acid and strong base titration, the equivalence point volume is always going to be at 25 milliliters. This is just an example. Okay, and remember that the equivalence point volume, that tells you how much titrant you needed to add to your sample solution in order to get to the endpoint. Okay, now when you're titrating a strong base, or when you have a strong base added to a weak acid, so in this case, something you're going to want to look out for here is these little dips. Okay, so a dip in a graph tells you that whatever you're working with is going to be weak. And since this has a lower pH, that tells us it's a weak acid. Okay, so since we have a pH that's below 7 and we have this dip, that tells us that our sample is a weak acid. Now, when you're titrating a weak acid with a strong base, your pH for your endpoint is going to be above 7. That's what you need to get out of this. Okay, so again, just to review, when you are titrating a strong base with a strong acid or vice versa, your endpoint will be at a pH of 7. However, when you're titrating a weak acid with a strong base, so again here, the strong base, that is your titrant. Your pH will be above 7. Now, for the other way around, if you have your titrant being a weak acid and your sample is a strong base, your endpoint will still occur above 7. Okay, so basically, if you're mixing a weak acid with strong base, endpoint will be above 7, whether your weak acid is in your sample or your weak acid is your titrant. Okay, now we're noticing here that at the beginning, there is no dip in the graph. That tells you that your sample is going to be strong. Okay, so if there's no dip at the beginning of the graph, which is when your pH is more closely following the pH of your sample solution, that tells you that your sample solution is strong. Whether it's a strong acid or a strong base kind of depends on where the pH curve starts out as. Because this starts out at 14, that tells us it's a strong base. Okay, so that tells us this is the sample. Okay, now for a weak base being added to a strong acid, we're going to have to draw our own curve here. So that's a pH of 7. So what's going to happen here for our curve? So because a weak base is being added to a strong acid, the weak base, that is your titrant. The strong acid, that is your sample. So that means the curve starts out low and goes high. Okay, and because we're starting out, or because we're mixing a strong acid with a weak base, that is going to mean that our endpoint is going to be below 7. So we got to draw the steepest part of this graph below 7. Well, actually, we'll try that again. Okay, so looking here, if I had to eyeball the steepest part of the graph, so the steepest part of the graph occurs there, and the middle part would be about there. So the endpoint would be there. The equivalence point would be about there. So the main idea is when you have a strong acid being titrated with a weak base, the endpoint pH will be below 7. Okay, and I didn't put any dips in this curve because our sample was not weak. Okay, but meanwhile, looking over at this pH curve, we do have a dip. Okay, and that tells you that your sample is weak, and because it's at a pH above 7, it's a weak base. Okay, which matches up with the title. Strong acid added to a weak base. Whatever is being added is the titrant. This is the sample. Okay, so again, the main idea here is that the pH of the endpoint is below 7 when you have a strong acid and a weak base in a titration. Okay, and then last but not least, we have a weak acid with a weak base. Typically, the endpoint for those are around 7. However, typically titrations with weak acids and weak bases together, they typically don't show up on the diploma.